Hi HSC folks. So if you're coming to this video right now, that means that you're pretty confident in your math skills and you feel really prepared to take the math section of the tax exam. So you're just doing some last minute prep through ConnectEd right now. If you're not sure how to sign up with ConnectEd or how to access your account, please just email me. But you should have been signed up for your ConnectEd account and have assignments assigned to you. And so the first assignment that you're going to see is under the umbrella of number sense and lesson 1.1, which is the complex number system. And so we're just going to cover this, right? Before you actually take your practice exam with those problems about the complex number system, I really highly recommend that you check through these notes that are posted on my website. And go through this video and actually try these examples for yourself, just so that you're super clear on what these questions are going to look like on the assessment and how exactly you should be answering them. So before we can even go into simplifying complex numbers, we first want to actually know what a complex number is. And so a complex number is actually just a number that's made up of two parts. So one part is your real part and the other part is your imaginary part. And we're going to go into more detail about what this imaginary part really means, but you actually already know what this real part means because you know what real numbers are, and everything that you've learned in math up until this point has only been dealing with real numbers. And so if we're thinking about the definition of a real number, it's really any number or value that can be found on a number line. And so this includes values like negative 3.5, negative 7 over 6, 0.3, 4, 5, repeating, square root of 3, and even pi, right? All of these values can be found somewhere on a number line, so it's like they're tangible, right? They're real. So we know that these are real numbers. And this should all seem fairly familiar with you because up until this point in your math career, you've really only been dealing with real numbers. You haven't really dealt with imaginary numbers, and we're going to cover why that is. So part of the reason why you haven't dealt with imaginary numbers is because let's say that you were in 8th grade or in Algebra 1 and you were taking the square root of something. You might have heard your math teacher say you cannot take the square root of a negative number. If you take the square root of a negative number, you did something wrong. In 8th grade in Algebra 1, that's not entirely incorrect. However, in higher levels of math, you actually are allowed to take the square root of a negative number because it results in something called an imaginary number, right? And we define this imaginary number as the square root of negative 1. And so whenever we have the square root of a negative number, we can actually rewrite it in terms of this square root of negative 1, right? When I think about something like the square root of negative 16, right? This is actually equal to negative 1 times positive 16. So I can actually rewrite this as the square root of negative 1 times the square root of positive 16. Now, this square root of negative 1, this is exactly our definition for I. So I'm just going to replace that negative 1 with I. And so something else I also realized is that the square root of 16, I can take the square root of 16 pretty easily, and that's going to be 4, right? And so I can actually just rewrite this as 4i. And we're going to go into some problems where we actually work with some operations with imaginary numbers, but I can actually just rewrite this square root of negative 16 as 4i using that definition of what my imaginary number is. Let's try another example with negative 8, right? This is the same as the square root of negative 1 times 8. So I can rewrite this as the square root of negative 1 times the square root of 8. And the square root of negative 1 is once again my definition of I, or my imaginary number. So this is really I times the square root of 8. If I want to get super technical and actually simplify this, I know that I can actually simplify the square root of 8 as 2 square root of 2. So this is going to simplify as 2i square root of 2. If you were confused about how I actually simplified square root of 8 into 2 square root of 2, there's going to be another video about that. Let's cover this one, right? We have square root of negative 6 times square root of negative 6, right? So I can rewrite both of those as negative 1 times 6, square root of negative 1 times 6, times square root of negative 1 times 6. I'm going to rewrite this as square root of negative 1 times square root of positive 6 times square root of negative 1 times square root of positive 6. So something I know is that square root of negative 1 is my definition for I, so I'm just going to rewrite that as I. I'm going to keep the square root of 6. And then once again, I see square root of negative 1, and so this is I again in square root of 6. So I see that I'm actually multiplying I by itself twice, so I'm going to write this as I squared. And then I see that I'm multiplying square root of 6 by itself twice again, so I'm going to rewrite this as square root of 6 squared. And I know that squaring something is actually going to be the inverse operation of doing the square root. So I know what's just going to be left is whatever is under the radical sign. So this is actually going to be 6 times, and then what's underneath the square, the radical sign, for I is negative 1. So it's going to be 6 times negative 1. And so if I'm simplifying this, 6 times negative 1 is just going to be negative 6. And so that should be my final answer. We're going to go over more about powers of I, but generally, whenever you see a negative sign underneath square root, you can just rewrite it as the product of negative 1 times whatever that value is, and then rewrite it with an I. So let's do some examples where we're actually classifying some complex numbers. So let's say that we're given this complex number 4 plus square root of negative 25. So I see a negative sign underneath my square root. So I'm actually just going to rewrite this. So I didn't do anything to the 4, but I'm going to rewrite this as square root of negative 1 times 25. I know that I can rewrite this as 4 plus negative 1, square root of negative 1 times square root of 25, just like how I did in my previous examples, right? And so when I do that, I can rewrite that square root of negative 1 as an I. So I'm going to do 4 plus I times square root of 25, which I know is 5. Okay? I'm just going to rewrite this where I'm writing my 5 before my I, just so that it's a little bit more proper. So I have 4 plus 5I. So I want to think about what is my real part, what's my imaginary part. And if we think back to the standard form of a complex number, A plus BI, A is whatever our constant is, or our real number. So that's going to be our real part. And then B is our complex part, our imaginary part. And so when I look at this, right, take a minute, think to yourself, what is going to be my real part given this complex number, and what's going to be my imaginary part? All right, you thought about it? Let's try it out. My real part is going to be 4. My imaginary part is going to be whatever that coefficient is for my I, and so I see that my coefficient for I is 5, so my imaginary part is going to be 5. And so written in standard form, following this form right over here, we actually already did it, right? So this is going to be 4 plus 5I. Let's try another example. Let's say that we're given this number 18.62. Now we don't have any square roots with any negative signs, so we know that we don't necessarily have an imaginary number. But just because we don't see an imaginary number doesn't mean that it's not necessarily there. So let's look at this. So we have 18.62, and if we think about 18.62, it most definitely can fall somewhere on a number line, right? So we know that it's definitely going to be real. So we know that it's going to be real. Okay. We know that we don't just see a value where it's a square root with a negative number underneath the radical sign. So we know that it's not just going to be imaginary. Let's think about whether or not it's going to be a complex number. So once again, right, we said that a complex number has a real part and an imaginary part, right? And so we know that the real part is 18.62. Now, we technically could have an imaginary part, right? The reason why we wouldn't see the imaginary part is maybe because our coefficient is 0, right? So we can have a coefficient of 0 for our imaginary part because this would just be 18.62 plus 0, because we're still following the 0 property of equality, where whenever we multiply 0 with anything, it's going to equal 0. And so that just equals 18.62. So we technically could have a complex number over here if our coefficient for our imaginary part is 0. So 18.62 is not only a real number, but it's also a complex number. take a minute, try out these two examples on your own, right? So what type of number is negative 296.2i? And then what type of number is negative 4.8 plus 56i? And then once you finish, press play on the video again to check your answers. All right, you finish? Let's go over it. So we have negative 296.2i. So we see this I part right over here. So we know for sure that it's imaginary. Because we see that I part, we know that's not going to be real. Let's see that, see if it would be complex, right? So remember, we have a plus bi as our standard form of a complex number. We do have this imaginary part, this negative 296.2i. And so one way that we could have an imaginary number is if that imaginary number were 0, right? So if a equals 0, then this would be classified as a complex number. So this is also a complex number. Let's see what type of number negative 4.8 plus 56i is. Looks like we have a real part, right? And we also have an imaginary part because of this I value. So in this case, it would just be a complex number. So when we're just summarizing, classifying complex numbers, we can actually see that all numbers can be classified as complex numbers. But not all numbers can be classified as real numbers or imaginary numbers. So when we're dealing with when we're dealing with imaginary numbers, there's actually something really interesting that happens whenever we raise our I to a certain power, right? And so when we have I to the 0th power, it follows the same rule that all numbers do that are raised to the 0th power, where it's just equivalent to 1, right? I to the 1st power also follows the same exponent rule as any number raised to the 1st power. It's just going to equal I itself, right? But then we start seeing some patterns that happen, right? And so I to the 2nd power, like we saw in that previous example, equals -1. I to the 3rd power, you can see in this expansion over here that proves this, it's going to equal -i. I to the 4th power is going to equal 1. Once again, you see in this expansion over here y equals 1. And I to the 5th power equals I again, right? And so this is where we really see our pattern start to repeat itself. And so a trick that you can do is just take the exponent of I, divide by 4, and the remainder will be the equivalent power of I. So let's look at an example, right? So let's say that we were given I to the, let's say 30th power. So if we were given an example of I to the 30th power and someone were to say, what is I to the 30th power equivalent to, right? What we could do is just take this exponent 30, right? So let's do 30. So let's do 30 divided by 4. Okay. So 30 divided by 4, I want to think about how many times does 4 go into 30? So 4 goes into 30 a maximum of 7 times, right? Because 4 times 7 is 28. And so 4 times 7 is 28. What's remaining is 2. So my remainder is 2. So I know that because of my remainder, I to the 30th power is going to be equivalent to I to the 2nd power. And I to the 2nd power is equivalent to -1. So if I'm simplifying I to the 30th power, it's going to equal -1. So when we're working with simplifying complex numbers, let's say that we're multiplying two square roots of negative real numbers, right? We want to first begin by expressing them in terms of I. And so we saw a previous example of something similar. Let's actually just flesh this out with more detail, right? So I know that I can actually rewrite the square root of -4. I can rewrite the square root of a negative number always as the square root of -1 times like the absolute value of -4, right? So this is going to be the absolute value of -4, which is 4. So I just rewrote square root of negative 4 as square root of negative 1 times 4. And I can do that with negative 8 as well. So I can do negative 1 times 8 instead of square root of negative 8. Okay, so because I have this negative 1 underneath, I can actually just rewrite this as negative 1. Let me just erase this to be a little bit smaller. Negative 1 times square root of 4. And then this is the same thing, square root of negative 1 times square root of 8. So I can actually rewrite these square root of negative 1s as i's. So I have I times square root of 4 times I times square root of 8. Okay. What I can do now is I know that the square root of 4 is 2, so I'm just going to rewrite that. And then I know that I can simplify the square root of 8 as square root of 2 times 2, square root of 2. Right, so let me just combine all these terms together, right? So I'm going to do 2 times I times square root of 2. And so when I do that, I get 4 times I squared times square root of 2. And I know from my previous slide that I squared is equivalent to negative 1. So this is actually 4 times negative 1 times square root of 2. And then 4 times negative 1 is negative 4 square root of 2. So this is my final answer. So remember, you can always just rewrite this, the imaginary numbers in terms of I once you just multiply out the negative ones. Another thing is if what's tripping you up is actually just simplifying the square roots, there's going to be another video coming up that will just go through specifically that skill, because that's going to be really important in the future. So there are some special properties that come along with complex numbers, and they're actually pretty neat, right? So you can actually add, subtract, multiply, and divide with them, as long as you just treat the imaginary part almost like a variable. So let's go through a couple examples where we're actually doing some operations with complex numbers. So if we're adding or subtracting complex numbers, we're just going to treat the imaginary part almost like a variable, and so we would just combine like terms like how we would for a regular variable. Right? So this is really 4 plus 2i, and I'm going to distribute this plus sign as like a positive one, so I'm going to be multiplying by positive 1. So this is going to be minus 3 minus 5i. And then when I just combine my like terms over here, I see that 4 and minus 3 are like terms. So 4 minus 3 gives me positive 1. Whoops. And then my other pair of like terms right over here are 2i and minus 5i. So 2i minus 5i gives me minus 3i. And so that would be my simplified complex expression. My next one over here is negative 3 plus 4i minus 1 times 5 plus 2i. So I'm going to, once again, just like distribute this negative 1. And so when I distribute this negative 1, I have negative 3 plus 4i, and negative 1 times 5 gives me minus 5. Negative 1 times positive 2i gives me minus 2i. All right, so what are my like terms over here? Right, my like terms are going to be negative 3 and minus 5. So when I combine them together, I end up getting negative 8. My other pair of like terms are going to be my complex parts, my imaginary parts, which are 4i and minus 2i. So 4i minus 2i gives me 2i. And so this should be my simplified complex expression. So why don't you try it on your own, where you're just adding and subtracting complex numbers. So you can look at the previous slide in order to help you with an example, but take a minute, pause this video right here, and when you're ready to check your answer, press play. All right, you tried it out? Ready to check your answer? Let's do it together. So I see that I'm subtracting these two complex expressions together, so I need to distribute that negative 1 to everything in my parentheses. So when I do that, my expression is negative 8 minus 7i. Minus 1 times 5, which is minus 5. Negative 1 times negative 4i is positive 4i. And so now I just want to combine my like terms. And so my like terms are going to be negative 8 and minus 5. Negative 8 minus 5 gives me negative 13. And then negative 7i plus 4i are my other set of like terms. Right? So negative 7 plus 4 gives me negative 3i. And so my complex expression is negative 13 minus 3i. When we're multiplying complex numbers, it's also fairly similar to when we were multiplying variables together. The only thing that you want to be aware of is your powers of I. So let's try out the first one. So I have 3 minus 2i times 5 plus 4i. You can approach this in a couple of different ways. One way that a lot of my Algebra 1 students really like to do is use the box method in order to multiply these out. You can also use something called FOIL. If you have another method, that's fine too, as long as you're multiplying all your terms together. So I'm going to use the box method for this because I think that that's probably the most common, commonly taught. So I have a box over here. I'm going to put my first complex expression at the top, so I'm going to put 3 minus 2i at the top. And I'm going to put 5 plus 4i on the side going down. And I want to multiply the sides of my boxes together in order to get what should actually be in each of these smaller boxes. So over here I'm multiplying 5 times 3 together. So 5 times 3 gives me 15. Over here I'm going to be multiplying 5 times negative 2i. So 5 times negative 2i gives me negative 10i. For this box over here, I'm multiplying 4i and 3, which is 12i. And then finally, for this final box over here, I have 4i times negative 2i, so that's going to give me negative 8i squared. And so I want to just take everything out of my box and just combine like terms. So I have 15 minus 10i plus 12i minus 8i squared. I see some like terms over here with this negative 10i and this 12i, so I'm actually just going to combine them to get 2i. And I didn't do anything to my 15, so I'm going to bring it down. This is positive 2i, so I'm going to make that plus sign. And over here I have this I squared, and I want to just be mindful of my powers of I. I know that I squared from that previous slide simplifies to negative 1, right? So this is really negative 8, and instead of multiplying it with I squared, I'm going to be multiplying it with negative 1. And so when I do negative 8 times negative 1, this is actually 15 plus 2i plus 8. And then I end up with another set of like terms over here, right? I end up with this 15 and this 8. And so when I combine 15 and 8 together, I get 23. And then I have my other imaginary part right over there to get my fully simplified complex expression. So this should be my answer when I'm asked to simplify that. Let's try out another example. I have 3 minus 4i quantity squared. So this is really the same as 3 minus 4i times 3 minus 4i. Once again, because I'm multiplying expressions together, I'm going to use my box method in order to help me multiply this out. So I'm going to draw a box, and I have 3 minus 4i, 3 minus 4i. And once again, I'm just going to multiply the sides of the boxes together in order to figure out what should go in each of these smaller boxes. So I'm first multiplying 3 and 3 together to get 9. And then I want to multiply 3 and negative 4i to get the product in this box. So that's going to give me negative 12i. I want to multiply negative 4i times 3 to get the product in this box, which is also negative 12i. And then finally, for this box, I'm multiplying negative 4i times negative 4i to get 16i squared. Remember, two negatives multiplied together gives you a positive. So I'm going to take out all these terms from my boxes and then start combining like terms when I can. So these are all my terms in my boxes, and I see that I have two like terms over here with this negative 12i, and that simplifies to negative 24i. I didn't do anything to my 9, and I didn't do anything to my 16i squared. Forgot that squared, right? But once again, like in my previous example, I squared simplifies to negative 1 when you actually expand it out. So this is really 9 minus 24i plus 16 times negative 1. And so when I further simplify this out, I have 9 minus 24i minus 16. 9 minus 16 gives you minus 7, minus 24i. And then this is your fully simplified complex expression. So why don't you take a minute to actually try this on your own where you're multiplying your complex numbers. press pause over here, try it on your own. When you're ready to go over it, press play. All right, tried it? Let's try it out. So I'm going to use the box method again because I'm multiplying expressions. Once again, you can use FOIL or whatever other method that your teacher might have taught you to multiply. But I'm going to use box method just because it's simplest as a visual learner for me. So I'm going to draw a box. I'm going to write 5 minus 3i at the top, negative 8 plus 5i on the side going down, and draw my lines to separate my terms out. And so I'm first multiplying negative 8 and 5 together, and negative 8 times 5 gives me negative 40. And then I'm multiplying negative 8 times negative 3i. Remember, a negative times a negative is a positive, so this should give you positive 24i. I have 5i times 5, so that gives me positive 25i. And then finally, I'm multiplying 5i and negative 3i to give me negative 15i squared. So I'm going to take out all these terms from my boxes and then start combining terms, like terms when I can. So I have negative 40 plus 24i plus 25i minus 15i squared. So once again, I have these like terms, 24i and 25i. And so when I actually combine them together, I get 49i. And I didn't do anything to my negative 40. I know that this 49i is positive. And then I didn't do anything to my minus 15i squared. Now I see a power of I, and so I know that I should probably simplify this power of I. And something that I know from previous experience is that I squared is actually equivalent to negative 1. So I'm going to replace I squared with negative 1. So I have negative 40 plus 49i minus 15 times negative 1. And so when I actually further simplify that out, I see that this actually simplifies to plus 15. I didn't do anything. This 49i, so let me bring it down. And now I have another set of like terms over here, right? I have this negative 40 and this 15. And so when I actually combine them together, I get negative 25. And then I have my 49i as my imaginary part to my complex expression. So that should be my final answer. When I'm dividing complex numbers, I actually want to use something called a conjugate, right? And so I want to take the conjugate of my denominator. And if you're not sure what a conjugate is, it's just changing the sign between the two terms in a binomial, right? So let's say that this is my binomial over here, 5 minus 3i. If I'm taking the conjugate of my denominator, my conjugate would just be 5 plus 3i. I'm just changing the sign. So whatever I multiply in the denominator, I also have to multiply in the numerator. And so this ends up being 3 plus 7i times 5 plus 3i, and then 5 minus 3i, and then 5 plus 3i. Now, if you have some scrap paper, I would really recommend that you do the box method to multiply out the denominator, multiply out the numerator, right? I'm going to do this for these examples, but then not when I'm showing you the solution for your check for understanding on the next page. But let's actually multiply these out, right? So when I multiply these conjugates together, something really cool happens. So I have 5 minus 3i, 5 plus 3i. So I'm just multiplying my denominators together. So I have 25, negative 15i, positive 15i, and then this gives me negative 9i squared. And so what I actually notice is that these middle terms cancel each other out. And so what I'm left with is just 25 minus 9i squared. And I have this power of I, this I squared, so I know that I can actually rewrite this as 25 minus 9 times negative 1, because I know that I squared equals negative 1 from my powers of I slide. And so this is really 25 plus 9, which is 34. And so what's really cool is that my denominator actually changes into, from a complex expression into a real number. Let's actually multiply our numerators out. So my numerators, when I multiply them out, it's going to be 3 plus 7i, and then 5 plus 3i. And so I'm going to multiply the sides together. So I get 15, 35i, 9i, and 21i squared. And so when I multiply these out and combine my like terms, I get 15 plus 44i plus 21i squared. Once again, I have that power of I, so I know that I can rewrite that as -1. So this is 44i plus 21 times -1, 15 plus 44i minus 21, and then 15 minus 21, which is -6 plus 44i. So this is really -6 plus 44i in the numerator. Now I can keep going, right? I can actually factor out a greatest common factor that I find between my real and my imaginary term. But for now, I'm just going to say that's fine, right? If I wanted to do that one step further, I noticed that my greatest common factor between -6 and 44 is 2, right? So I can factor out the 2 to get -3 plus 22i. And then I know that 2 times 17 gives me 34. My 2's cancel out. And so I can actually just be left with -3 plus 22i over 17. And then that would really be my fully factored and divided out expression. Let me try out the next one, right? Once again, I just want to multiply the numerator and denominator by the conjugate of the denominator. So my denominator is this 5 plus 2i. My conjugate, I'm just going to change the sign from a positive to a negative. So instead of being 5 plus 2i, it's going to be 5 minus 2i, and then 5 minus 2i in the numerator as well. So when I do that, once again, I'm going to use my box method. So I have 5 plus 2i, 5 minus 2i, so this is 25 minus 10i, plus 10i, and then minus 4i squared. So this is really 25 minus 4 times -1, which is 29. So my denominator changes to just being 29. And then my numerator, I'm going to use the box method again. I have 1 minus 4i, 5 minus 2i. So I get 5 minus 20i, minus 2i, and then plus 8i squared. So this is really 5 minus 22i plus 8i squared. Once again, I see that power of I, so I can rewrite that, right? So I have 5 minus 22i minus 8 is what it's going to simplify to. I have my like terms 5 minus 8, so this actually simplifies to -3 minus 22i. So this is -3 minus 22i. I don't actually have a common factor between my numerator and denominator, so I can't divide anything out. So this would be my fully simplified form. So why don't you try it on your own, right? You want to divide out your complex numbers using your conjugate pairs of your denominators. So take a minute to just pause here. When you're ready to check your answer, press play again. Let's check out our answer, right? When I look at my denominator, -8 plus minus 7i, my conjugate pair is actually just going to be -8 plus 7i. The reason why I didn't change that -8 is because that -8 is just term. I'm really just trying to change the operation from subtraction to addition or addition to subtraction, right? And then I'm going to multiply the same value in the numerator. And the reason why is so that I'm not actually changing the fraction fundamentally, because I'm actually just multiplying by a clever version of 1, right? I'm actually just trying to simplify it using this clever version of 1. And so when I multiply these together and multiply my conjugate pair out, I get the following. I said that I wouldn't multiply this out in the answer, but I'll just do it just so that you have something to refer to, right? And you can check your work and see if you got anything wrong. So I'm going to do -8 minus 7i on this side, and then -8 plus 7i on the top for my box method. I get positive 64, negative 56i, positive 56i, and then negative 49i squared. And so this equals 64 minus 49i squared. I have that power of I, so I can replace that with negative 1. And so this is really 64 plus 49, which is 113. And so 113 is my new denominator. My numerator, I need to, once again, do the box method. Multiply out the numerator, the original numerator, negative 1 plus 5i with the conjugate of the denominator, negative 8 plus 7i. And so when I do that, I get positive 8 minus 40i, negative 7i, and then 35i squared. So when I take out these terms, 8 minus 40i minus 7i plus 35i squared, I'm going to combine these like terms to get 8 minus 47i plus 35 times that power of I is negative 1. And so this is 8 minus 35 minus 47i, and 8 minus 35 gives us negative 27 minus 47i. So that's going to be my new numerator. So now that you've finished watching through this fairly long video, make sure that you're completing your assignment, Number Sense 1.1, the complex number system. If you want more practice problems on this before you actually do your assignment, to kind of assess your readiness on questions like this on the tax exam, you can check out my website in the tab Test Prep. There are going to be links in the description bar as well for just more practice problems. And as always too, in the notes at the bottom of most of the slides, I cite where I pulled these problems from. So if you just click those hyperlinks, you should be able to find a worksheet with very similar problems to kind of test out your skills. So good luck. If you have any questions, make sure that you email me or message me through my Google Voice number.